Yep.
But it's the sun setting too.
Yes.
Fourth. Okay. You want the arrow? Or?
Off that direction. Rainbow.
Back to the sun. Yeah, you're back to the sun.
Oh, yeah, solar.
The fourth one. That'll probably work. There we go.
Is this the page they go to for getting started?
Yeah, and then you could actually.
Like the basic haiku would be this one?
What is it? I think there's a. Actually, well, that's the description. Maybe the. You want to start them from something? Yeah, you could maybe pick one to start from. We could make it. We could create a really simple one now to start from. Maybe that.
Well, let's go here.
Mm-hmm.
Team Storms Development.
Is it what's called about?
About, or what is it? I think was the tag.
Let's see. Let's go back here.
You could click on haiku editor. You don't need to create a haiku.
If you can check the string.
Hello, testing 1, 2, 3. Oh, you
Did you
gotta check.
email me URL?
I emailed it to the group.
Let me see if I can catch it at this time. I have no group email in my email queue yet. Okay, while that's percolating through, could I impose upon you to send it directly to forther@comcast.net, please, at this time?
It's a very thin little.
Just a cover. Here we go.
Let me wake this up.
Oh, there's an email from some flounder. At 4:04 p.m.
Hmm?
Are you in a different time zone, Dennis?
That would explain the echo.
It says 2:09, but what says 2:09?
You versus. I don't know that. I guess that is you.
He had two copies of YouTube running at the same time. It looks like that's what my problem was.
Did you have 2 copies of
I don't think so. God, I hope not. That would be really embarrassing if I just grounded everything to the station.
Are we getting a feed?
Weird.
Shall I blather on? That's something. La di da di da. Why didst thou promise such a beauteous day, and make me travel forth without my cloak, Let base clouds o'ertake me in thy way, hiding thy bravery with their rotten smoke. 'Tis not enough that through the clouds thou break to dry the storm from my something or other. For though thou repent, yet I have still the loss. Ah, but thy love your pearls, or but thy forgotten that class. Anyways. Ooh. Something. You think there's audio coming from the camera? Ooh. Are we good?
It sounds like it's in clear now.
So then,
Listen.
Okay.
so then the question is, shall I join it or shall we leave it alone?
I would say leave it alone and get on with the
Yeah,
show.
I think so.
Finish up your talk.
Yeah.
Sounds good. All right. Well, I hope that is not an indication that joining the talk was the underlying problem. But
No, I don't think it was.
Have you-
Although
you've
we
changed-
had both mics on. That was initially.
initially.
problem.
Okay.
Yes. But now we know I've got to do some more work on setting up
Okay.
the next one.
Okay. Do you have some sense of what you did?
Yeah.
Good.
Tell us.
One, mute, yes. 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 The other is disable my mic and then start the broadcast.
Oh, really? You have to disable
Oh.
before you start the broadcast.
Oh, how interesting.
Ha, 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 ha.
Write that down.
Okay.
Tips.
All right. Well, to round things out, let's see. We got so I was going through and looking at some of the recent ones just to keep the folks up to date. Here's another small animated one. Let's see. What else have we here? What in the heck is this? Somebody mutated the Running Man. Some sort of apple. More of this. This is interesting. This is fairly terse. So anyways, I would encourage you to check out my blog. Maybe if I get comments in particular, that will motivate me to write more and check out the haikus. The Yellow Way. Other fun ones do we have? Are there any questions about Discuss or my blog or haikus?
Are you still getting a lot of interest in people making new ones?
So I'm definitely getting a stream. Whoa, what's this now? I'm definitely getting folks adding more haikus. I've been surprised given the amount of effort required to do a haiku. I mean, granted, many of them, like this one, I happen to know is a derived work. I'm a little surprised I haven't had more comments on the haikus, but I've had some. So I'd say there's, maybe every month on the order of like 50 to 100 postings, depending on the month, of haikus. And then so far there haven't been that many comments, but there's been a little bit of back and forth. I think it's been kind of weird because previously the people posting the haikus, there's a small collection of them. One fellow Manwei from Russia, and then there's this Dark Star fellow. I gather he's in London, maybe. And then there's Stainless, who's also in London. There's a kind of a spectrum of them, and previously their only mechanism of communication was the haikus, and so I think it's a little weird now to be, okay, I could post something in plain text and have it come through. So yeah, the interest seems to, that's an interesting question. I could actually take a look at the level of traffic I've been getting here. Let's take a look. So If I go to, actually no, I want to go here. Let's see. So if I go look over 30 days, I've been getting some amount of traffic. What is this in? Queries per second. 41 queries. That can't be right. Front end instance hours. That's a fair question. I don't think this interface gives me a good way to answer that. What I should do if I wanted an answer to that is there's a bunch of different services, including Google Analytics, that I can install that would let me track that with better graphs. That's just the raw, like, usage data for App Engine. But yeah, my sense is that there's a core body of them that periodically post, and they're a lot of them are from the demo scene community. So what their real motivation is that they want to produce a very small program that does something, and so the haikus are kind of a means to an end for them. And so I think they show up when they've got some idea as to how to make a small program that does something they haven't done before, and then they post a series of them. Mm-hmm.
Let's say I wanted to look at a very basic one like text.
Okay.
And I bring it up, and just to view the thing in the first place.
Okay.
And I'd say, okay, that's a simple source. I think I might be able to reach the point where I understand it. Then I wanted to make a change. So I go to the editor. Is there a way to get that source code into the editor?
So this link down here, create a derived work. And if you click on that, then you go straight to the editor with that, with the text of it ready to go. And it defaults to the title being the previous title, Redux, and then the author defaults to anonymous. So then you have the opportunity to create something. So then say you think, oh, well, this is nice, but I would like to make it yellow. I can make a change, and then now it's yellow. You hit update. And then when you're ready to publish, you can publish as in that way. This one's interesting. Actually, this one's particularly interesting. They have a big chunk up here that's just commented out, so that's not even. Let's see.
So that doesn't show until you get into the editor?
Which the
stuff that's commented out, or was it there?
No, it was there. It was there. If you go back here, you'll notice there's some trends around the top portion of it.
No, I see it.
Yes. Yes, it is fourth after a fashion.
Could you go back to the source, the original?
The original, yeah.
Yeah, just back one. So I can get the capitalization right in this PowerPoint.
But yeah, I think.
Where does it select the color?
So the color is the way it's being generated is that this function is being run once for each pixel, and on the data stack at the end you're expected to have RGB. If you only have one value, then you just get red. If you have two values, you get red and green. If you have three, you get red and blue. So, for example, the way I made this one yellow is that I assume that because it's all red, it's just a single value on the stack. So then I just added dupe at the bottom, so that whenever they're having either a 1 or a 0 on the data stack, and so I'm just duping it so that there's then either 0, 0 or 1, 1, and then you get all red and green all the way up is yellow. And similarly, if I added dupe, then I should get white. Alternatively, I might do something like I could add the X and Y value and then put a gradient behind it, that sort of thing. Or what else could I do with it? I could redefine X in terms of and y in terms of a cosine and sine. Oh, I didn't do what I wanted. Let's try that.
Whoa.
Whoa.
But it went off the screen.
Yeah.
You had it.
Whoa.
There he is.
Let's see. What else can I?
Scaling's a little bit high.
Yeah, let's see. Let's do a divide instead and see what that does. We know that's going to do it. How about?
There he is.
There he is.
He's on a little bit longer, but you still got a lot.
Yeah.
Your periodicity.
Yep. Let's see. I do this and then. Wait, no, I want. And some. Oh, that's. Oh, I should mention it goes magenta if you've got a bug, which is not the most. If there's a stack overflow or anything like that. What am I doing wrong here? Ah. Okay. Well, that didn't do anything good. All right, let's try this. That. Anyways, I'm being.
Ooh.
Oh, that's what I did wrong. T.
You got an extra colon. You left the colon.
Oh, I left the colon. There we go. Whoa, that didn't do it. Whoa.
There he is.
There he is. Whoa.
Your period is still. Whoa.
Whoa.
That's what you want to do.
Yeah. Let's see. What if I do?
You want to swap spigots and
Yeah.
iterate this getting started?
Yeah. There we go.
PowerPoint live or?
Sure, we could. Let's do that. Are we live producing a?
I think that's a worthwhile ambition.
Okay.
I don't know how you feel about it.
Sounds good.
Now I have to go back to.
Give him the mic.
Oh, yes.
Thank you, sir. A round of applause to thank Brad for his. Okay, be that way. Let's mute the YouTube stream here. I want to close the 2-minute Grand Canyon version. All right, so there'll be a short delay while I fiddle around for get this up on the screen and try to that's interesting. We know what the little note here. I wonder what the maximum resolution of this thing is. Yeah, I think if I bring this one's twin brother that doesn't have a camera, could we get it on the Hangout and use that as the monitor during fourth day?
Yeah.
Will that?
Yeah.
And it's just a plain old Wi-Fi. La-di-doo-da.
The audio's the hard part. The videos, I see the video.
You think you do?
Here's my audio.
All right. Well, Thank you, all of you who are watching this, for your patience. Consider yourselves as being folks that are contributing to the next month's 4th day and the hopeful escape from complete debacles and disasters. And so I switched to the dual presenter XVGA mode. Now my screen is black and that screen is black, and I don't know what the heck to do now. The last time I reached this point, I just had to reboot.
That's the you can get some. Where do you go fix that? Well, I think
There's actually a device in most prescribing eye doctors and opticians' office where you take a pair of random glasses, plop them in, and they will map the optics and tell you what the prescriptions of various elements in the progressive lenses or the trifocals or whatever are. And all I can say is, must be magic. If you think about what it takes to do that.
purely analog.
Is it really?
It's an analog system. It has to be. Well,
No, it's a focal plane and a light source. But is it like a point that scans, or is it like a
I've been
field of...
watching that happen. It's only been a few years that they've had that.
8 or 10 in my eye doctors that I see infrequently. It's really annoying. You can tell eye doctors till you're blue in the face, I do not want any mail, phone calls, or other contact from you until I decide to come back. Thank you very much. And then, sort of like a year later, you requested that we contact you. No, quite the opposite. No, it's just that they can't imagine somebody that doesn't really want to hear from them.
No, they want money from you.
Well, that's all to the good.
Hurting for money.
Well, the problem with going to the cheapest is that that guy isn't really the very best optometrist or eye doctor that you can find. Yeah, that's a good question. You know, I guess maybe he doesn't, but it reminds me of a truism. You know what they call the guy, you know, at the top of the, maybe it's sometimes guys or gals, at the top of the medical school graduating class, you know, summa cum laude, magna cum laude, all of those designations. You familiar with those?
Yes.
Are you guys familiar with the title that they award the last place academic standing medical school graduate?
Same as the top.
Doctor. They call him doctor, yes.
Both called doctors.
Somehow, without my directing it to switch, it managed to say, oh, I want to put it up on the big screen. And all it took was to reboot in the middle of this. And rather than start Firefox, which is a mistake, I should have just started PowerPoint. So it will take me a minute to get back into PowerPoint. I guess I wanted Firefox going. More to the point, I guess I wanted Chrome going. So let's wait until PowerPoint gets going, and boy, something's bogging it down. You ever get one of these things started and say, you know, I could probably do without Norton Antivirus? Okay, so that's my first slide. Fourth haiku, getting started. Brad, where is this? Where is the list of fourth vocabulary words? Is that? Yeah. Okay, it's not on the what is it then?
Actually, yeah, there's a full glossary that this is from the what is it page. At the bottom of the what is it page, there's a one-line list of all. The glossary has it all.
What's it called?
Glossary.
Yeah. Aha. So let's go back to this. And somewhere here it should say, what is it, right? And
That list is all the words there. This glossary has.
okay.
And if you click on each word, there's actually an example.
Is that the right word, hot link? What is it called when you hypertext, hyperlink?
Yes, that's even old. Hypercar.
I actually have a copy of HyperCard. I think it's still sealed in plastic.
That's Stone Age.
I'm pretty sure I have a computer that will run it also. Okay, so what I'm going to do is take the coward's way out. And just popping the link into the doohickey. So I think that the next thing I want to do on the next screen here, on the next PowerPoint slide, is go back to the hexagon. Create a derived work. Can I delete this after I've... Now I just click update and it'll run. So let's go back to the PowerPoint. And strangely enough, it looks like it all fit. I think that's all to the good, yes. Oh, now it made it bigger. Yeah.
Really want a good clipboard manager? You should download SourceForge, a program called Ditto. It's bloody amazing.
Yeah, the problem is that I can barely keep track of what's on the stack, never mind what's in my clipboard manager.
Well, no, it's a stacked clipboard manager.
That's my point.
And you can select from, up to 50 to 100. You can have it clear out every number of pages. You can share it with computers.
Yeah.
It's quite easy. Just,
No, I take your point, yes. So, is this enough to get somebody started?
I think it might be helpful to describe sort of the idea that
Think of the program as being, something that's going to be run once for every pixel in the image, and that you're being given X, Y, and potentially T for time. And so your goal is basically to write an expression that it ends up with reflecting you on the stack at the end, given X, Y, and T.
Old enough so that I don't have to register it or get Microsoft's permission to run it. I merely plop the CD into one computer in my house. This happens to be that one computer. I have a license, I paid for it, and I don't have to get it blessed or authenticated or authorized or registered. It just runs. What is it called when you have to, get your piece of software approved by Microsoft?
stolen.
Well, no, there's a term for it. And there's a guy that wrote the secrets book, and he said, I'm not writing any more Windows secrets books, because product activation has put me off of all Microsoft products. I'm not going to do it anymore. I've had enough. And product activation, yes.
Right. These days, even the activation, you do not own it, you borrow it.
Now, don't get me started about things like what, Photoshop now, where the program isn't even on your computer anymore. It's on the cloud.
Well, so is Office now. Office does the same thing.
Not my copy of Office, duh.
One does, correct.
Well, that's why you don't get open source now and.
This is why I would,
You can get, in fact, I prefer open office to the current office.
so once a year I send Christmas cards. I like to put the barcode on the address label. Microsoft Word does that. This copy of Microsoft Office does that. It sucks in a data file, prints envelopes with a barcode. I feel like I've accomplished something. I could probably write a program that would do that, but life is too short. Somebody has already done it.
I'm just curious which one it is.
Which? Microsoft Office.
Yeah, this one.
That is like,
What the hell about?
that's probably Microsoft PowerPoint.
Look under help. Help about is 2000. Yep.
This is Office 2K, yes.
Okay.
I'm not sure if this was the last version that didn't require product activation, but I am sure that this is a version that did not require product activation. My criteria were twofold. Barcodes, and no product activation, and this does both of those just fine. Thank you. If you can convince me that somehow the latest, greatest version of Office running on other operating system from this one, if I may say, it probably won't run on this one. Okay, so the program runs once for each pixel. Is that something that Brad wanted to say? X and Y.
True. And it would be secure.
Yes.
Okay. Is this something that's said in the about on the what is this?
It is said, it is actually, so perhaps that's.
Okay.
Yeah, there's no and.
And there's no comments.
There is no comment. Correct.
How about spaces?
There's no spaces either.
Yeah, there you go.
If you dare mention it for animation, if you think that as animation is T gives you a time value.
Oh, that's true.
That's how you deal with this one. All those required in the simple matter of having T.
You don't need time. Well, doesn't the image just a solid?
Yeah, you don't use T. Right. I'm saying all those required to add animations. Yes.
So for the one that you did the gradient, what was the phrase that you used? Just X and Y at the end?
Yeah, it's used X and Y.
Yeah.
That's actually very nice and very simple. You're looking for something even simpler than X.
So did it automatically shrink? I guess it did. That's good. That's what I wanted.
probably want that to be a lowercase t. Can't remember if it's case sensitive. I think it's not.
Yeah, that's more a function of the program deciding that it wanted uppercase.
No, I realize. I think it's actually not. I think they didn't make it case sensitive because I actually have entered haikus in my phone. I was concerned with it. Normally, I find case sensitivity excellent.
So you do this on your smartphone?
Yes. You have a sufficiently an iPhone or my phone. In some cases, it actually works better than phones. There are a set of drivers that are blacklisting these security issues on desktop. So even on some machines, literally just
Is it a reasonable use of the comments feature to ask for help or clues or suggestions?
These days, I would say you might be able to use the forum, actually.
Form?
The forum.
Oh, that's what I meant, the forum.
At the bottom, yeah. And if someone posted there, I would probably, this one I might go to some response. But I thought you know, the comments on the hikers themselves, which until, you know, I had discussed forum was in fact the only way to do it. Yes.
Which is like,
Well, in fact, what
is
people,
that insane?
what people would actually do is they would post a haiku and then it would fall off the top and they'd post it again. You know?
Yeah.
So it's a recent haiku. Right. Bad.
Oh, you can have, I guess, like filter, right? You know,
How many there are?
right. The thing is, you can post some comments. Or,
Yeah. No, in fact, actually, consider this.
Because you're just having whites right now, right?
In the counter, the Discuss forum actually supports, in addition to embedding the forum, you can also per ID embed a count. So because they're keeping the data for how many comments, you can actually have, if you have like an index where you showed it on all news, you can conceivably put a little thing in the corner showing how many comments there are. The primary reason I didn't do that is right now, most of them not be zero. It's
Well, maybe it encourage people to post.
that's true. I should consider it.
I mean, assuming it's not
Yeah, no, well, it's not my
or technically break something.
Yeah. No, well, it's that the beautiful thing about Discuss is it's not my research. It's their,
Can you do something about program?
oh, so the site I've got it actually on is Appian. It's Appian and it's sort of
Okay, so what we're going to do now is take a break, since that seems to be what we're good at. And we'll be back in a few minutes, hopefully, with our afternoon's under your name there.
Okay, can people show, when I want to show something physically, where do I stand?
That's a good question.
Oh, Dennis, Earth to Dennis. Yes.
If he wants to show something,
Physically, where do I stand?
you want to move the camera for it, or you just want to stand where you want me to go?
Well, I will stand here, and you put marks on the floor, and I'll stand there.
I want to pick it up into the light so we can see it. There you go. And that can sort of, yeah, we can see that.
Okay. And then I'll go to the presentation, and I'll maybe talk to this.
Basically, anything in front of the screen will be on the broadcast.
I see. So
Where I'm going. So just put it anywhere in front of the
So
screen.
you won't, if I'm sitting over there, you won't see my head, but that's okay. You'll hear my voice.
If you want to show your head,
Yeah.
rather than me going back and forth, this is easier. Just walk over in front of the screen.
Okay.
We have your head.
Okay, so say, everybody shut up. No, that was me, I'm sorry. I wouldn't think that you'd be that rude. The first thing you want to do is say your name and then
Let's start the
start
date.
in.
Okay, ready?
We are ready.
Okay, so my name's Harold Raby. It's October 24th, 2014. And I'm here to talk about porting forth to the RCA 1802. So it's a blend of two 1970s technologies. The RCA 1802 first came out in 1976. I don't know when Chuck Moore's forth, I think it was 69, but it got really popular around the mid-70s. So these are kind of two technologies of the same era. And let me say up front, my interest in forth is more like a techno-archaeologist. I certainly don't intend to write applications in forth, but I do like to write compilers. I've written 2 more compilers than I've written forth applications. So this is one of them. And it's like the challenge of getting a completely self-hosted development environment in a very resource-limited technology of that era. This particular board I'm showing here is an RCA 1802 evaluation board, and it has 10 1K bit RAMs on it. Okay, so we're talking about 1.25 K of RAM. And this is the kind of resources that are available in that era. This particular board, if I expanded it completely, would have come out to 4K of RAM. Wow. The processor is here. The 1802 processor, as I said, came out in 1976. This particular one on the board has a date stamp of 7653, which is the 53rd week of 1976. It turns out 1976 did have 53 weeks. And I guess the elves at RCA were busy cranking out chips just before Christmas or just before the new year, and I got one of these. This board itself dates from 1979, I believe. I picked it up at a garage sale, believe it or not. And let me show you the development environment that comes with it. I got it in my bag here. This is the development environment. This side is the assembler, and this side is the disassembler. And that's what you get. You get a list of opcodes, a list of hex numbers, and some pseudocode explaining what each instruction does, and the rest is up to you. It's a simple matter of programming, right? So this is what you have to start with. So let me kill that menu. So the challenge is to fit a self-hosted compilation environment into a very resource-limited technology like this, and it's standards-based. So I did not go out and reinvent the wheel in forth. I know forth is the kind of thing that everybody likes to have their own flavor of it. I didn't want to get into that side of things. I said ANSI 94. Let me stick with that. It is what it is. I'm not going to be, politically in favor or against it. I'll just do what it says because at least it's documented. And ANSI 94 did a good job of separating functional requirements from implementation details. That's the first time that really happened. Up to that point, the forth literature is full of descriptions of forth technologies which had confused together how it was implemented with what it was trying to implement. And the 94 standard separated those 2 issues. So let me see if I can move on with this. Okay, so the 1802 came out in 1976. It's static CMOS, which was brand new at the time. Intel and the other microprocessor vendors at the time were doing NMOS. CMOS is much lower power. It's totally static. In fact, It's so static that you can run this thing at 0 clock. And one of the ways you can debug code on this kind of level is to stop the clock. There's a switch here that says step mode. And every time I press that button, I get 1 clock. And I see the pins on the bus change, and I see there's an array of LEDs here. And you get to debug your program by stepping through the clock cycles on the processor, you know, and figuring out what's happened on the bus and seeing whether the bits have the right value. So totally static. Very low power, 10 milliwatts. That's low even by today's standard. If you open a PC today, you'll find a desktop PC, most of the weight is heatsink. This thing doesn't need a heatsink. It runs very cold. And another advantage of very low power is it went into space. So obviously in space, you don't have hunking great batteries. You don't have a lot of power. And the other reason it went into space is because it's radiation hard. So 1970s is, you know, the height of the Cold War. Getting electronics into space is very important for national defense. And I don't know what designs this got into, but from the civilian side, it was designed into the Galileo spaceship, which went out to Jupiter. I think it was launched in '89. And I just looked it up. They crashed it into the surface of Jupiter about 10 years ago. So there are a lot of these sitting in, you know, at the bottom of a hole on Jupiter somewhere. And you can still get it. You can still get it. Intercell makes it. I got a current data sheet. It's about a year old. You know, government designs don't go out of fashion very quickly. I'm sure somebody's still got to make that same circuit board that went into space on the Galileo. They still have a contract to make that, so you can still buy it. It's not cheap, of course, because it's a very, very low demand part, but it's still available. So this is the chip. It's 40-pin DIP. Again, DIPs are almost out of fashion nowadays. And just want to point out from people who are coming to forth from a, you know, a hosted environment running under Linux, running on a PC or running on some kind of environment, this has none of the stuff you can rely on when you're in a hosted environment. There's no disk. There's no file system. There's no keyboard. There's no video out, there's no VGA, there's no mouse, there's no Ethernet, no Wi-Fi, no USB, and there's not even any serial I/O. So what you see is what you get. You've got 8 bits data bus, you've got 8 bits of address bus, which are multiplex. That means you have to have another chip to get the whole 16 bits of address space out. You've got 4 input bits, and you've got 1 output bit, the Q bit. So kind of the hello world of RCA 1802 programming is to turn that qubit on or off and watching an LED flash. If you can do that, you're a programmer, okay? So that's really what you get. And so the challenge is, what's that?
I'm channeling.
Okay. It did have a feature, it does have a feature, by the way, which allows you to load memory by toggling some of these control bits and setting things on the data bus. You can actually load memory without any other interfaces. And somebody sells a board with 8 switches on it and a push button and an RCA 1802 and a little bit of RAM. And you set the switches and you press the button and that loads location 0. And you set the switches again, you press the button and that loads location 1. And then you press another button and it runs. Yes, so when you get to location 10 and you realize you made a mistake at location 1, you have to start all over. So that's the kind of I/O device that comes built into the RCA 1802. Everything else you have to supply. Okay, so remember, when people say, why don't you have a floating point, you know, disk file system? That's a good reason. So what are the registers? It's kind of interesting. It was a real oddball in its day. I mean, the Intel and MOS technology and Motorola had their own 8-bit processors at the time. And they all had a typical architecture of, you know, 1 or 2 accumulator registers and a bunch of CISC instructions. This didn't have any of that. It has 1 8-bit accumulator, and everything is done in the accumulator. All the arithmetic is done in the accumulator. So you've got 8-bit arithmetic only. That's it. You do have 16 registers, and you'd be tempted to call them general purpose, but they're not general purpose because you can't even do arithmetic in these registers. All you can do with these registers is point at things. So you load these registers, and you have to load them a byte at a time because everything has to go through the D register. So you have an instruction to copy the D into the low byte of R8 and then get the high byte of R10 back into D. Everything goes back and forth between these registers. And if you want to refer to memory, you have to use these registers. This, by the way, is very like RISC. So ARM processors today do exactly the same thing. You can't refer directly to memory. You have to load an address into some register somewhere and then use that. So this is how this works. So if I want to refer to memory, I use, say, what's called the index register. There is just one. I can make one memory reference, and there's an X register which selects one of the 16 pointer registers. So if X contains the value 10, then R10 is my index register, and then I can load from the address pointed to by R10. If I want to load to a different address, I have to change R10 or change X or something. But here's where it becomes interesting. That's as it may, but the thing that's interesting, I can also select which is the program counter register. And I've never seen that on any other architecture before. On every other architecture, you may have general purpose registers, but one of them is always dedicated to be the program counter. Here, I can pick any one of the 16 registers to be the program counter. And that's what saves me when I get to do forth, because I have no subroutine calls. But I have the ability to change the program counter register is what allows me to do the inner interpreter and all the other stuff in forth. Okay? So if P contains R7, then R7 fetches the next instruction, points to the next instruction, it gets fetched, it gets incremented, and I execute that. The only register that's special here is R0, and that's because when I power up, P is set to 0. So when I turn the power on, I hit the reset button, P is set to 0, the contents of R0 are set to 0, I start fetching from location 0. That's the only special function that any one of these registers has. Okay? So if I want to do arithmetic again, so I have to point the X register to one of these these pointer registers and then reference memory via that register. Okay. Okay, the instruction set fits on a piece of paper this size. Very simple.
The center of the white
Yeah.
area. That's your assembler, your disassembler, and all that.
Okay, this is my assembler on this side, upside down. Here's the instructions and the encoding and the decoding. Here's actually the pseudocode of each instruction, what it does. And this is the disassembler. I can look it up by opcode and figure out what the instruction does. Okay, so it's got 1 byte long. Well, when I say most instructions, all instructions are 1 byte long. Some of them have an immediate operand right after them, but they're all 1 byte long. Most instructions take 16 clock cycles, 16 cycles per instruction. This chip, according to the data sheet, runs at 3.2 megahertz, which means I have 200,000 instructions a second, or 5 microseconds per instruction. This thing here is probably, the clock is running at 1,000 times faster, and it's probably doing 10 instructions per clock, not 16 clocks per instruction. So architectural improvements have made this thing, you know, orders of magnitude faster than this technology. The only arithmetic I have is 8-bit. The D register is the accumulator, the DF is the carry flag or the borrow flag. And I've used up, out of the instructions are basically divided into a 4-bit opcode. And most of the instructions have a 4-bit register that specifies one of the registers. So out of the 16 possible opcodes here, I blow away 11 just to address the various, those 16 general purpose registers. So here are 4. So load to get high, get low from the register, put high and put low. In other words, get or put D register into the top half or the bottom half of one of the index registers. Here's a load instruction. That's how I get data from memory to the D register. Here's a store. That's how I get data from the D register to memory. And here's one that is helpful when we're doing forth, which is load and advance, which is load memory from the register referred to and increment that register by 1. So I lied when I said there's no arithmetic. There's actually an increment. You can do an increment on the implicitly on one of the index registers, on one of these registers using load advance. I can increment and decrementing it, the register. And here are the 2 interesting ones: set the program counter and set the index register. Now, I don't know which guy in marketing signed off on this, but this has a sex instruction. And it is what it is. Okay. There are branch instructions: short branch, conditional, branch on 0, branch on non-zero, branch on carry, and so on and so forth. And it's not even very friendly if the branch can only go within the same page. So you find yourself, you know, you add a couple of lines of code to your program, and suddenly a branch destination is a different page from the branch origin, and you have to change it into a long branch. So the assembler is a little bit hairy. I'll move my code around, you know, and insert some gaps or whatever. So. But these short branches, all these instructions are 16 cycles. If I want to do a long branch where I have 2 bytes of destination, then it's going to cost me 24 cycles to do a long branch, and then I can branch anywhere in address space. So there is a long set of conditional long branches too. So that's the instruction set. So not a lot to learn when you want to write programs for this thing. So it doesn't have a call or return. I have a branch, but it doesn't remember where it came from. I mean, the whole purpose of a call return is you make a branch, but you remember where you came from. It doesn't have that. But it does have this set program counter, and we'll see how we can use that to simulate kind of call return. It doesn't have any stacks in hardware. And that actually is kind of like RISC nowadays. RISC processors don't have hardware stacks. You have to push and pop your return addresses manually on RISC processors today. No arithmetic between registers. All the arithmetic is in the D register. It's 8 bits only. If you want to do 16 bits, you have to diddle with the carry bit and do it a half at a time. Forget about 32 bits. There's no I/O. So to do I/O with this thing, you can obviously put a chip on it. You can use there's 1 output bit and 4 input bits. If you recall, on the processor, I can do bit banging and do serial I/O. But what I'm going to do in the demo is actually use a host OS and simulate I/O. So I'm going to cheat on the I/O side. Even the UART, this RS-232 may be unobtainable in a couple of years too. I mean, already you can't find it on PCs, but you can get the adapter. In 10 years' time, I bet you won't even be able to find the USB to serial adapters anymore. So this technology is, what? Yeah, same. But today I can get USB to UART. That may not be available in 10 years because nobody may want it anymore. So even if I had to try and do bit banging or UART, I may still be stuck and trying to find something that will connect to it. Okay, so to put forth onto it, I want to minimize execution time. I want to minimize space. Obviously, space is a premium. And kind of the 5 routines I'm really worried about are next, of course, and basically the words that introduce the different kinds of high-level definitions, colon words, constants, variables, and created words. Also, exit is a very common instruction, returning from a 4th word and pushing a literal onto the stack and manipulating return stack, getting stuff on and off the return stack. So these are the kind of things I looked at when I was figuring out how to design it. How do I lay out the parameter stack? Do I do it big endian, little endian? This machine doesn't really have any endianness to it. There are no 16-bit data types that this thing knows about. So it's really up to me how to organize the endianness side of things. So the stack will go up or go down. And finally, the question, should I do indirect, direct, or subroutine threaded? Now, when I started this, there was a FIG-4 port for this thing. And the FIG-4 model is only indirect threaded. And it worked. And well, what fun is that? Somebody else wrote it. I want to write my own. So I threw it away and said, I want to do it better. I want to do it direct threaded because it is faster. And the direct thread is definitely many clock cycles faster than indirect threaded. So let me explain how the set program counter instruction works because we're going to be using this a lot. Let's say right now the program counter is set to, the P register is set to 1. That's the 4-bit register that selects which of my 16 registers is the program counter. So if the P register is set to 1, then R1 is my program counter. R1 points to a location in memory, which is the next instruction to be executed, and it happens to contain the instruction to set the program counter to R2. So what happens? R1, this is fetched. P gets set to 2 because that's what the set P instruction does. And now suddenly R2 is a program counter. And R2 contains 5, 6, 7, 8, and now I'm executing from a different location in memory, 5, 6, 7, 8. So that's like a branch, but the interesting thing is the R1 remembers where it came from. So after I've incremented R1, after I executed set R2, R1 points to the next instruction past where it came from. So that's how I remember where I came from. It's actually not a subroutine call, it's a coroutine call. This is some technology that people had heard about in the 50s, forgotten about, but there's a thing called coroutines, where 2 pieces of code call each other back and forth and remember where they came from. It never made it into any high-level programming language that I know of, but it is a known concept. So the SEP is good. It's only 1 byte, which means I get short code. But the bad thing about SEP, I only have 16 different options. There's only 16 different things I can put in, in the register field. I can only pick one of 16 registers. But it turns out that is okay with Forth, because Forth really only has 5 things that you have to do, maybe 4 things that you have to do. High-level words are one of 4 different types, and that's what I use 4 different registers for. So let's look at the stack design. There is a load and advance instruction, as I mentioned. So that's obviously a candidate for pop. And that means that I want my stacks to grow from high to low. Because when I load from R1, LDA R1 will take R1, load the location pointed to by R1 to the register, and increment R1 by 1. So that will mean that my stacks, both of them now grow from high to low. It would be nice if there was a decrement and store, like the PDP-11 has, but it doesn't have a decrement and store. It actually has a store and decrement. Okay, so it did the store first and then decremented. I can kind of use that. And the other thing is it only works on the particular index register that I'm currently selected. I can't do a store and decrement on every register. So if I want to use STXD, what I normally do is set the X register to be the parameter stack, because most of my stack activity is on the parameter stack. And so I will set X to be the same as the parameter stack pointer, and I'll be able to use STXD to do some pushing. But it's not as nice as I say, some other architectures. So this is the top of the stack, grows from high to low. So now let's talk about threading. We got direct, subroutine threaded, direct threaded, and indirect threaded. Subroutine threaded says I have a machine instruction called subroutine call. I just made it up, and my code is a list of subroutine calls. If I compile a colon definition foo, which contains A, B, and C, it contains a call to A, B, and C, and then a jump to the next routine. Can't do that with the 1802 because I don't have a call instruction. Direct threading, well, direct threading, my very first instruction in the colon definition is machine code, but then the rest is addresses of other words, or execution tokens of the other words to be executed. So that's the direct threading mode. And I only need a limited number of these. I need one for colon, I need one for constant, I need one for variable, and it turns out I also need a separate one for create. And I'll go back to create and why create is a problem. But I only need a limited number, except for the create case, which is when you can do a does, you can override the runtime action. So that's, I'll go back into details of that. And finally, the indirect threaded, which was the FIG force model, where the body of the or the code field was also an address of a runtime routine. This makes doing create does a lot simpler, but it's much slower. First of all, it's larger also. This is 2 bytes, and that subcall is a SEP, so that's 1 byte. And secondly, if this is a machine code definition, actually it's 2 bytes. I need an extra 2 bytes to point to the next location. And in the case of direct threading, I don't need any prologue to do direct threading. I just write machine code right in the body of the word. Okay? So it is longer, and it is, of course, slower. So I picked direct threading. So here's a direct threading example. So let's say I have a constant. I've defined a constant, 1, 2, 3, 4 constant. I called it foo. The compiler creates some kind of header, the dictionary header, and then it compiles a SEP instruction, and there's a reserved index register, which I've symbolically called the constant program counter. It's used whenever there is a constant word compiled, and followed by the data. So 1, 2, 3, 4 has a constant, a set to this routine, and followed by the actual constant data, which in this case is hex 1, 2, 3, 4. And this is actually stored big endian. The way my assembler, it's actually an assembler that decided to store it big endian. It's not really any real property of the architecture. It stores the 1, 2 first, and then the 3, 4. So when I do a set constant PC, const PC is pointing to this routine called doConst, and it loads, it knows that I've come from the code PC, which is 0. It has to know where I came from. And so it can use the pointer, which is now here, to load the constant value. So it loads in via the code PC register, decrements the parameter stack pointer, and stores that value on the parameter stack, and incidentally takes the advantage of decrementing the parameter stack pointer, loads the low byte of the constant, the 34, stores that on the parameter stack. Now, my const PC is now pointing down here. If I want to use it again, I have to reset the constant program counter because I can't call it again. So I actually branch back to the instruction before the const PC, and then now the constant program counter is pointing here, ready for the next time a constant needs to be executed, and I can do, and then I go to my next routine. So that's how I compile a constant word. Okay, so this is the basic concept. There is a little routine like this for each type of fourth word there is. There's one like this for const, one like this for colon, one like this for variables, and one like this for create. Okay? What about the stack endianness? So if you saw it back here, I actually stored the stuff on the stack. I pushed the high byte first, and that was really because, how do I go back? I pushed, just so that I can avoid manipulating the, getting these bytes in order, I pushed the 1, 2 first, and then the 3, 4 second, so the high byte is below the low byte on the stack, on the parameter stack. Now when I'm storing a double, I started doing all this stuff, I wrote all the single words, and then I ran into this statement in the standard, which says, the cell containing the most significant part of a double cell shall be above the cell containing the least significant part. So the standard prescribes that you have to store the doubles in a particular order. It doesn't leave it up to you. So it turns out that means I have to store a double, I have to mix the endianness up. This is the high cell, and this is the low cell, so it's mixed up. It turns out not to be that bad. There's not a lot of double arithmetic, so, and it's perfectly standards compliant. You don't have to store it one way or the other. It's called mixed endian. Okay. The return stack could be either way. What I decided to store it was the opposite way from the parameter stack, just so that I could do to-r and from-r just by doing this. So to-r and from-r work without having, I reverse the endianness of the return stack relative to the parameter stack. So here are the dedicated program counter registers. Whenever I enter a word, when I get to the execution token, or the CFA, what it used to be called, I have to be using R0, which I call the code PC symbolically. I have to be there. So one of the requirements of every word that changes control is to make sure that the program counter is set to R0 when I enter a word. The inner interpreter is R4. That's the next. That's obviously the key part of any fourth symbol system. Then I have a program counter for words created with colon, one for words created with constant or value, one for words created with variable or create one. I'll mention what create one is in a second. One for words created with the word create. User is not an ANSI fourth word, but it's kind of a traditional word that from years ago for variables used by the compiler itself. I don't know why it's called user, because they're actually used by the compiler. And it turns out the word execute, which has to pop up an execution token off of the parameter stack and put it into the program counter, I actually have a whole register just devoted for that particular word. So there's a register. So each of these is, again, a loop of code that essentially does its thing and jumps back to the entry point before so that I can call it. And these are the lengths of each of these. Next is 6 instructions long. Colon is 12 instructions. That includes, pushing the IP back onto the return stack. Const and var are both 7 instructions. And create is a monster at 15, and I'll explain why. And this is so on and so forth. The fourth virtual machine has just 3 registers, the inner interpreter pointer, the parameter stack pointer, which is equal PSP. And since most of the arithmetic is done on the parameter stack, I by default set the index register to be the parameter stack so that I can do my arithmetic, get data to and from the D register using the index register. So right at the beginning of initialization, I have set the index register to 2. And of course, 2 is the right number for sex. Everybody knows that. Okay. And then there's return stack. So this is the virtual machine. Here's next. Next, you have an instruction pointer, which is, I call it the IP. And it points to a list of execution tokens in the body of the fourth word. And they're still a big endian. So the high byte of the execution token is first. IP is loaded into the execution token is address of machine code, so I put it in the code program counter. I set the IP, I put it in the low byte of the program counter. I branch back to here to set the next program counter back to this location again, so I can call next another time. And then I go to whatever's I've just loaded into the code program counter. So that's next is 5 instructions. And this by far is, if you profile a fourth program, you're spending 60, 70% of your time in these 5 bytes of code, or these 5 instructions. This is a variable. A variable is similar to constant, except instead of pushing the contents of this location, it pushes the address of this location, so that's a variable. Okay, now here's the problem with create. Oh, first of all, you guys probably know what create and does do. Is that grammatical? Okay.
So it's like you call builds does.
Well, here's the problem. I have a problem with I have a problem with builds. Builds went away, and that's one of the things I think was a mistake. The standards committee did some good stuff, but I think that happens to be a mistake. I'll explain why. So here's an example of how you might use create and does in ANSI forth. There is no builds in ANSI forth, only create. And if you're in modern day terminology, you've defined a class with one method. And the default method is push the address of the body, and it can be overwritten. So you can define a class with one method, and you can change what that method is if you don't want the default. In the case of a variable, that's what I want. I want the default behavior. I can't go backwards. In the case of variable, I want the default behavior, which is to push the address of this guy onto the parameter stack. But in the case of create, I want to override the default behavior. So here's the issue. If I do a create, I put a header, it compiles a header, and then I have to compile a call to some set routine which will take care of the, of the semantics of the thing I've just created. And then I have to put a pointer to a piece of code which is the runtime behavior or the method of this class. And by default, it's no-op. No-op means just do the default behavior, which is push the address of the data field. But this can be overwritten. So this is a case where I've compiled this. This no-op just points to a next. But later on, when I come back and I see it does, I go in and overwrite this location with something else. But here's the body of create. It's 15 instructions. I have to do this, and I have to fetch this, and I have to indirect it, and I have to put it in the program here. Anyway, it's a lot of work. So that's what create does for me. But most of the time, if I don't override it with does, I don't need all that stuff. I can just use variable or something similar to variable. So that's where I invented a word called create one. So here's my understanding of what happened. In FIG forth, you said, if you wanted to use does, you said builds first. You said, this is a sign I'm going to be overriding this thing with does. ANSI forth says, well, builds looks very much like create. So we'll merge the two words together and we'll just have one word called create and there is no more builds. So that's what ANSI forth did. That, at least for this architecture, creates an implementation, a restriction on the implementation. When I see a create in the compiler, I do not know whether it may be overridden by does or might not be. In FIG forth, if I saw a create, I assumed it was not going to be overridden. But if I saw builds, I knew it was going to be overridden. So in FIG forth, when I saw builds, there's usually a does. When I saw a create, there's usually not a does. In ANSI forth, I only have create, and it may be used or might not be used. And to be standard in camel forth, which is the one I'm talking about, I have to assume that the does may be used when I see a create. But if I know ahead of time that does is not going to be used, I use this other word, create one. And I get much faster execution because I know that there's not going to be a does part if I use create one. So actually, I've defined variable in terms of create one. Variable is actually create thing saying that I'm not going to be overriding it. I allot a cell, meaning there's a space for the variable pointer. I mean, the variable data, and that's how I use create one. Okay.
Why didn't you just call it builds?
Because it's the opposite from builds. Create one is you may not override it.
Why didn't you call create one create?
No, because that would break the standard compliance. I got to be standard compliance.
Why? I'm sorry. Go on.
Because it's a good question. Because I can leverage all the other stuff that standards compliant. I don't have to write everything from scratch. If everybody's going to, give me code that complies to ANSI forth, I can use it here. It's not true that everybody does, but I've done that in some cases. Okay. So I actually put up a question on comp.lang.forth about this, and Elizabeth rather did not get my point. So okay. It's like how many architectures have this problem? Just mine. Yeah. Yeah. Oh, I don't want that.
Just minimize it.
Do I have to register for university to talk here?
No, just to,
Can I get a degree?
classes. Right. No, seriously, unless you want to use your browser, you don't have to register.
No, I don't. Okay, so here's my rant. I'm done about ranting. That's it.
So just to be clear, you couldn't just not have VA1 and waste it somewhere. Just to the word.
And time, a lot of time. 15 instructions instead of 5. Yes, I do have create. And when I'm doing, standards compliance stuff, I have to use the create. But if I'm writing my own code, I use create one. So what's Camel Force? Camel Force is actually an ANSI-compliant force compiler that was written by a guy called Brad Rodriguez out of Canada. Brad is into minimalistic architecture stuff. He designed a processor architecture. Everybody's heard of CISC, complex instruction set, RISC, reduced instruction set. He designed an architecture called PISC, pathetic instruction set. And I think the goal of that was to, could you actually build a CPU with 7400 series LSI? Is it actually within the realm of possibility to hand build a CPU nowadays? And I often ask myself the question, what is the minimum number of, let's say, gates plus bits of memory needed to build a standards compliant fault environment? The RCA 1802 is pretty minimal. And it's, I can see why the architectural decisions were made. They were made to reduce gates. In the days when that thing was designed, they probably drew the schematic on a piece of paper. Who knows how they designed it, right? They had challenges of their own. So it's pretty minimal in terms of its architectural support. And nevertheless, I can get a force compiler in 4K, a fully standards compliant force compiler in 4K, which I think is interesting. Anyway, so Brad wrote this a compiler. He wrote it originally started when the standard came out. He did Intel 86, of course. He did another 8-bit Intel micros, some Zilog micros, Motorola. He's actually spent a lot of the time on this thing called the TI MSP 430. I don't know if you're familiar with it. It's interesting little things. The 16 bits, modern, still made. I know it's very kept up to date by TI. And it's very like a... Okay. Right. And I like, it's very much like a PDP-11, which is, I think one of the best architectures ever built. And, it's this thing, but 34 years later. And then now I put RCA 1802. So he has a website, and you can get this compiler from his website if you want. Okay, the dictionary is pretty standard. It's a single linked list. It's simple. It's pretty poorly performing in terms of speed. A linked list, he wastes a whole byte on the immediate flag. I don't know why. That's one of the first things I want to fix when I have time, is to get that immediate bit into, one of the bits in the count byte. That will save me 1 byte per word. That's a lot when you only have a K.5. And then it's direct threaded. So after the name, you have the code field, and the code field is one of 5 different things. It could be just assembly code, things like dupe, wrote, plus, 0 equal, those kinds of things. It could be colon word, which is a set to its colon program counter plus a list of execution tokens. It could be constant or a value. Value, it turns out, has the same compile time semantics as constant in this system. And it could be a variable or create one. In the case of a variable, it would be just 2 bytes of body data. In the case of create one, it could be any number of bytes. And finally, the case I hate, which is the create case, where I have to have a set plus an execution token for the does part plus the body data itself. So it's longer and slower. Okay, so these are the 5 different kinds of code fields that I could have in the dictionary. So I just plowed to the standard, trying to implement everything I could. The standard is divided into word sets. There's a set of core words. There's 133 of them. I did them all, including the obsolescent ones. There are 46 core extension words. I did them all except for 3 of the obsolescent ones. There's some double words. I did 3 of them. 3 of them turns out are needed by the compiler, so I needed those. I didn't do the rest. There are a set of words called programming tools. I did them all except the disassembler, which is called C. That's not simple to write. And then there's a programming tools extension. I did not do the assembler or the editor. And I did not do all the hard stuff. Like the floating point, the search. This is, I guess, what used to be called vocabularies. The blocks, which used to be the old file system way back when. Exceptions, I don't know, files, heap, all that hard stuff is not done. But what I did do is made sure that it passes the ANSY's test suite. You're familiar with John Hayes' ANSI test suite. I think there's a later version. I'm working with 0.7. I think there's a later version I need to try it. There's a 0.1 version, right? What? 1.0, yeah. Who? What's that? Oh, marker, yes, marker's in here. I also did forget. So forget is easy when you have a single linked list. That's why they got rid of it. My understanding, they got rid of it because once you have more than one linked list, you can't do it easily. Marker, I guess, saves the state of all the lists, right? But marker, you have to have hindsight in order to use marker. You get to a certain point and say, oh, I have a bug back there. I wish I'd have put a marker. No, but I did forget as well. And that, by the way, those test suite is what I use for regression testing. When I run the demo, I'll actually run these test suite. I know it. Every time I put what I think is an optimization, I run this and I find out whether I've horribly broken things. It's a quick test. Some statistics. There are a total of 275 words as of today. 91 of them are in assembly code. Oh, but 2 or 3 are very simple, those. There's 9 of these user variables. There's a total of 163 colon words. Some of these are just standard NCC. Some of these require what used to be called kernel knowledge. In other words, manipulate the internal data structures of the compiler. But today it's 6.5K. I've just got it all sitting in RAM and simulator. But I have created a subset that's able to bootstrap the rest of it. And the subset is less than 4K, which is interesting because now it fits in one of these ROM chips. So I can load, if I can get this actually has a 2K version of, this has a 2K ROM, but the same socket will take a 4K ROM. I can put the bootstrap subset in here and then put the rest in RAM and actually compile it on the fly after boot time. By the way, so I forgot to mention, I did try to bring this up yesterday. It has a ROM in here. So the label on the ROM says Cosmon 24th of October, 1980. So the bits in this ROM are 34 years old. And that actually could be the explanation for why it didn't come up yesterday. These bits do rot. You know, they are electrostatic charges on gates. And, you know, a few electrons a week. And pretty soon you can lose a bit after 34 years. I think the official spec duration is like 10 years. So, and the same is true of the flash cards and your USB drive. So if you intend on bequeathing your USB drives to your great-grandchildren, refresh them every 10 years. So the bits don't rot. Okay, so 4K is kind of a magic. If I can get it down to 2K, it would be even better. But there's a challenge there, which is the performance. There is a challenge. So I did some performance measurements. I actually wrote a piece of code that counts the 64K. It puts 0. I didn't mention this. This is a 16-bit force compiler. Duh, yeah, it's not 32-bit. So I can count to 16K. I just basically increment a 16-bit number until it wraps to 0. And it takes 1 plus dupe, 0 equal question branch. These are the instructions. These are all machine code words, of course. And there's 1, 2, 3, 4 incantations of next. Next is 6 instructions. This is 17, 23, 34. So a total of 58 instructions around this loop. And 64K loops, if you do the arithmetic at 3.2 megahertz, takes 19 seconds to do this. I can actually, my simulator tells me how long it takes. My simulator keeps track of clock cycles. In machine code, I can do the same thing in one of my 16-bit index registers. I can increment it and test it for 0. When it wraps to 0, and it takes about 3 instructions per loop. So it takes less than a second to do 64K loops. So the ratio, I don't say this represents any and all benchmarks. It is one number. But fourth to assembler is 19 times slower than assembler. No, dude, this is even worse. I got to do arithmetic each time. This is just a 0 equals. a plus loop, I mean a loop, a terminating condition is a lot more work than a zero equals. Okay. I mean, take it for what it's worth. It's a benchmark. So, okay, before I get off to that point, I calculated how, I measured how much time it takes to look down the, to look through the dictionary. The dictionary has how many words? 200 and something words in it? 275 words. So the most time-consuming part of any compilation is looking through the dictionary to see if the word's already defined. If the word's not already defined, I've got to go all the way to the end of the dictionary, and it takes about 1 million cycles to search through the dictionary. If I look for a non-existent word, it comes back after 1 million cycles, which is 1/3 of a second. This is real time on the hardware, 1/3 of a second. So it's not trivial. It's because I have a singly linked list. You know, if I get 1,000 words, it will get even longer, of course. 1 million cycles, which is 16 cycles per instruction. I'm going to do the math, 60,000 instructions. Okay, complexity, the size of each of the words. The blue ones are the words that are written in as colon definitions. The longest one turns out to be the else. This is the bracket else, the thing that does the conditional compilation thing. It's a piece of code I stole. I think it's in the standard. I just compiled it in. The next hairiest one, or the really hairy one to take, this is the one that took the longest to write, is /mod, unsigned multiple /mod. This is a big piece of assembly code. Remember, I have 8-bit instructions, and I have now to handle a 32-bit divisor, a 16-bit dividend, a 16-bit remainder, and a 16-bit quotient. A lot of shuffling going on, right? Because everything has to go through that silly little D register. So that's why it's a lot of code. It can't be coded in fourth. It is the multiply instruction of the machine. /mod is the multiply instruction. It's all the other arithmetic is based on this. // is based, all call this eventually. So that's the lowest level of the multiply, of the arithmetic. Yeah. /star is slightly less complicated. That is the 16 by 16 to 32-bit multiply. A little bit less to juggle, but still, you know, I'm handling 16, 16, and 32. I'm handling 64 bits of data, all in and out of that little 8-bit D register. Call is complicated, is actually quite large. It turns out most of that is the sign-on banner, believe it or not. You know, the thing that says, welcome to fourth. And here's some other things, move. So that's kind of what it takes to implement it. So here's the demo. We'll come to the demo in a second. I've got a cross-assembler. So I write the thing in assembly code. There's a cross-assembler. Luckily, there's a free one now that you can download. Somebody bought, I don't know if it's GPL, I don't care. You cross-assemble it on any kind of C compiler. Sorry for mentioning the word C, is that okay? It produces an Intel hex file, which is the machine code bits. It produces a listing file, and I extract, the simulator extracts the symbol table out of the listing file so I can do things symbolically when I'm debugging it. And I load this into simulated memory, I load this into simulated memory, and I start executing at location 0 like the real hardware would. And the only things that I cheated is when I get to read from the input, or what's it called, the standard input. It's the word in force is called accept. I actually have the simulator supply that from a command line on my host. And similarly, when the simulator needs to output a character, when the machine needs to output a character, it sends it to the host, to the simulator. So these are the two words that are implemented in the host and not in forth itself. So what are the advantages of simulation? I'll show you some of them in real time. First of all, I get some error checking. Forth is really nice for implementers. I looked through the standard. I could not find one place in the standard where it said you had to check any errors. You don't have to check for any mistake that the user makes. Everything is, what's it called, ambiguous condition. That's great. I mean, what do they say? You can make demons fly out of your nose if it's easier to compile that.
Never heard it out on my nose.
So there is actually one error message in this compiler, which is can't find the word in the dictionary. But anything else you do, you said it, you got it, right? If it doesn't do what you think, read the friendly manual. It will say implementation defined. Sorry, not my job. You expected to do something, you know, reasonable, not my job. I had to make it simple, right? So there's no error checking. But the simulator can check for things like underflows, which is nice. That's a common error. Stack underflows. Every time I return to the simulator, you know, I check the two stack pointers. I can check when somebody's trying to stomp on my compiler. That's probably not a good idea. I can check for that. And also, if somebody jumps to a piece of, you know, random data memory and tries to execute an undefined opcode, I can check for that. I can do tracing. This is really how I debug most of the thing. I have a tracing option in the simulator. I'll show you how that works. Again, all outside of Forth. It's not in the Forth environment. It's in the host. And I can do it at the Forth word level. And it shows you the contents of the stack, or I can do it at the machine code level. It gives me cycle-accurate timing measurements. It's a bog-simple timing model. It's either 16 cycles or 24 cycles. None of this nonsense with cache and, you know, TLB misses and all that bullshit you have nowadays. You can't figure out how long things take to execute. Here, it's very simple. And it turns out, even on a, you know, not state-of-the-art PC, it's actually 600 times faster than the real hardware. And that's without even optimizing it. What? No, it isn't. Yeah, you send this thing into space, it would die instantly. You're quite right. It's not red hard. All right, so let me go to the demo.
Then again, neither are most of the production 1802s.
Oh, they're not?
No, at one time, RCA and then Harris had a red hard, like CMOS line. And I think that most of the ones were produced that correct substrate, that feature size, and other optimizations in the process that led to space qualified. But most of them were just run-of-the-mill. And in some closets, in some places, there are still stocks of those parts for people that want to apply them. It's sort of discouraged to use parts like that. I think they'd rather fly an Actel recent vintage. You know, so you can plop your 1802 core on an FPGA and fly that and get approval easier than NT parts. Yes. But you know, there are fewer and fewer red hard lines as time goes by. I think that,
oh, the communication satellites guys got to have that stuff.
yeah, well, that's Marconi.
Right, they've got to have it.
But it's just this shape.
So can everybody see that? Should I make this font bigger? Is that okay? Okay, so here's I'm going to run the simulator. Let me just show you what I'm going to simulate. That's the object code of the core. That's all the words. So that's called Intel Hex. And I will basically load that into the simulator. And here's, you know, I've signed on, and if I say words, there are my words. Okay, so that's my 275 Forth words. If I want to run the regression tests, that's the Jerry Jackson's tests. Like tests. Basically, I concatenate up here. There's tester.fr is his test framework, and then there's a bunch of .fth files which contain the tests themselves. I just pipe them into standard input of the simulator, and then look at standard output and get rid of all the noise that comes from the OK prompt that comes back from the Forth outer interpreter. And basically, I run all these tests and they will pass. So that's how I do my regression testing. So let me show you now how tracing works. Okay, so very simple. I'm going to write a word. So there's a word called trace that turns on symbolic tracing. And I'm going to create a word called foo, which runs a loop. I'm going to put a 10, 0. I'm going to do a do. I'll turn on tracing. I will fetch the index, I'll drop the index, I'll loop back, and I'll turn off tracing. So I'm going to do count from 0 up to 10. And here, since I've turned on tracing at the beginning of the loop, I will see here, this is the number of instruction cycles since I booted. So I've already executed 6.7 million instructions. This is the address of what I'm about to execute. Since I'm executing this word foo, it's all past the end of the dictionary. So that's the last symbol that this simulator knows about. This is the word I'm about to execute. You know, xdo, it means get the I index. Do a drop, an X loop, which compares to, the top and the bottom and the loops back. Does that 10 times, and when I'm done, I get out. So here's the return stack. The return stack has got quit at the bottom of it, then the interpreter, and then it's got the number 10. The return stack, the trick is to put the loop control onto the return stack. It's got the number 10, and then here I put the count between where I am now and how far to the end of the loop. It's a standard trick for when you have a machine that doesn't have sign compares. And so this is the return stack, and here's the parameter stack. I pushed that I, and then I dropped it, and I pushed the I, and I dropped it, and so on. So this is how tracing works, okay? And it's very helpful for, obviously, for finding logic bugs in force code. Let me just turn on one more thing, which is the machine code trace. And you see that when I turn on machine code tracing, I'm seeing now every instruction of the processor, the location, the instruction, the D flag, the D register, the location, the memory pointed to by X. It's basically for debugging machine code words. Okay, so there's no GDB, obviously, no debugger, but you work backwards and figure out what went wrong. All right.
Now, are you logging up the stats of the execution of the instructions someplace?
Like for what purpose?
You were showing as far as time.
I'm just keeping track of the number of clocks. Every time I execute an instruction, I add 16 to the number of clocks, and it shows up in the fourth level tracing. It shows up in the leftmost column that we turn on fourth level tracing. Hold on, this is the instruction level tracing. Okay, now that was how long it took to turn off fourth level tracing, and here's the number of cycles since boot here. So when I said it took 1 million cycles to search through the dictionary, that's how I knew it.
Well, I think that we'll round of applause. Look forward to this one.
Thank you.
It's still available for download?
Brad Rodriguez's site has it. I can send it to you. His is fairly old. I can give you the latest one if you give me an email address.
Have there been any changes to the PDF that you sent?
Yes, this has got new material in it.
Would you send the
And there will be more changes before fourth day too.
updated version of what you presented today?
Okay.
I sent you Dave Jaffe's email address.
Okay.
He keeps an archive of the meeting notes.
Got it.
And it would be good to have this material available to casual passers-by in their dwells.